Welcome. In this video, we are going to look at using the integral test to determine the convergence or divergence of this series. And before we can use the integral test, we need to know and understand how the integral test works. Why might we choose to use the integral test? Well, if my function appears easy to integrate. And this function, while it doesn't appear easy to integrate, is relatively easy to integrate. So we're going to look at that, but anything I would give you on the test would be a lot more apparent that it would be easy to integrate. So given a sequence with positive terms, if we treat that nth term, my a sub n in this situation, which is 1 over 2 to the power of natural log of n, so we're looking at that sum from 1 to infinity, if that a sub n term, we treat it like a function. If the function is continuous, positive, and decreasing for all values of x that are positive numbers n, then the integral in this series will both have the same behavior. So we're going to take a sub n here and we're going to treat it as a function of x, 1 over 2 to the natural log of x. And then we're going to treat it like an improper integral. So we're going to plug it into that function. If the improper integral diverges, then the series will diverge. If the improper integral converges, then the series will converge. Before we do anything else, we need to verify that the function is continuous, the function has all positive terms, and that the function is decreasing. How might we show the function is continuous? Well, showing it's continuous is showing that the domain is all real numbers, or at least all real numbers from 1 to infinity. Okay, so if I plug in numbers, natural log of x, that's where my variable is. Natural log of x only exists to the right of x equals 0, so positive numbers on the number line. So that means at a very minimum, we could have, if I plug in 1 here, if I plug in 1, I could get natural log of 1. So that would be 2 to the natural log of 1 power, or 2 to the 0, which would be a positive number. All other index values of n that I plug in larger are still going to give me positive numbers. So the domain is all numbers greater than 1, because 1 is the smallest number I can plug, greater than 0. That would be the smallest number I can plug in. So it is positive, it is continuous. Another way that we can think about showing something is positive or continuous in this instance would be to look at the graph, and I'll just slide over here my graph. So I've plugged in the graph of 1 divided by the quantity 2 to the natural log of x power, and I already changed my window a little bit. But what you can see looking at this, and this graph actually continues up forever, it has a vertical asymptote here at x equals 0. It is continuous, there are no breaks, it is positive, and you can see that it is decreasing. Before we do anything else, we're going to talk about how we can show it is decreasing. So continuous, we can look at the graph or consider the domain, and in this instance, check they both work out. Positive, that would be consider the terms, and all of the terms are always going to be positive. There's nothing that is going to create a negative term here. And then when we look at decreasing, that would be taking the derivative of this function. You can also show that the nth plus 1 term is always going to be less than the nth term, but in this case, I'll deal with the derivative. So in order for me to deal with the derivative, I'm going to rewrite my function, f equals 2 to the negative natural log of x. That negative natural log of x, that is 2 to the natural log of x to the negative 1, or rather 2 to the natural log of 1 over x. So that's my original function, and rewriting it like this makes it easier for me to differentiate. I'm going to delete this little picture here so I have more space to talk about finding my derivative. All right, so once I find that derivative, f prime of x, well, the derivative of something exponential, that is 2 to the power times natural log of 2, since the base is not e. And then we have to say times the derivative with respect to x of natural log of 1 over x. So furthermore, we have to deal with that little derivative piece in there. The derivative of a natural log composition, I have f prime of x is 2 to the natural log of 1 over x times the natural log of 2, and then the derivative of a natural log is the derivative of the argument. The argument there is x to the negative 1 over the argument, 1 over x. So the derivative of x to the negative 1 is going to be negative x to the negative 2. So I have negative x to the negative 2 divided by 1 over x, or x to the negative 1. And so negative 2 minus negative 1 is negative 1. And that's going to end up being negative 1 over x. So I have f prime of x equals 2 to the natural log of 1 over x times the natural log of 2 times negative 1 over x. So basically, when we look at this function, everything in here, this will always be positive. This term is a positive constant. What about this term? Because of that one negative, it will always be negative. Therefore, the derivative is always less than 0, and we can assume that it is decreasing. And showing that something is actually decreasing is important to prove. I will be looking for that on your lab and or your test. So now that we've done this and we've solved this problem, we can apply the integral test. So applying the integral test will involve treating this function or solving it such that it's an improper integral. So I'm going to rewrite this as an improper integral with bounds from 1 to infinity. So the first thing we do, we cannot solve an integral with infinity in it, so we're going to rewrite that as an improper integral, the limit as b goes to infinity of the integral from 1 to b, and then I have 1 over 2 to the natural log of x power dx. At this point, in order to solve this problem, we're going to do a u substitution. So I'm going to say let u equal natural log of x. If u equals natural log of x, then du is 1 over x dx. Furthermore, I just need that dx there. That means x du equals dx. Now, I'm going to end up with an x in my problem here, but what is x equal to in terms of u? X equals e to the u. So the last thing I'll do before I move on is I'll change my bounds. U equals natural log of b, that will stay as it is, and u equals natural log of 1, which simplifies to 0. So doing this u substitution, now what I have is the limit as b goes to infinity. My bounds have gone from 0 now to the natural log of b, and I have 1 over 2 to the u. Natural log of x is going to be rewritten as u, and dx is equal to x du. Now, I can't have x in my problem, but what is x equal to in terms of u, x we've found is equal to e to the u. And that makes this integrable. So I have the limit as b goes to infinity of 0 to the natural log of b. These are different bases, but they're both raised to the same power. So I have e to the u over 2 to the u, which is the same as e over 2 to the u du. And the integral of an exponential function, if it's base e, would just be that exponential function. Of course, this base is not e, so we need to divide by natural log of the base. And I have the limit as b goes to infinity of e over 2 quantity raised to the u power divided by e over 2. Sorry, divided by natural log of e over 2. I misspoke there. So like the chain rule, when we're doing derivatives, we multiply by natural log of the base. When we're doing antiderivatives or integrals, we divide by natural log of that base. That's a constant, which can come out in front. Let me just put, we've got u equals natural log of b and u equals 0. So this is 1 over the natural log of e over 2 times the limit as b goes to infinity, and I have e over 2 to the u. Again, u equals natural log of b to 0. At this point, we plug in natural log of b, and we plug in 0. Of the limit, let's not leave off that constant multiple in front, 1 over the natural log of e over 2 times the limit as b goes to infinity of e over 2 to the natural log of b minus e over 2 to the 0. And e over 2 to the 0 is going to go to a constant. Anything to the 0th power is 1. So we end up with a 1 right there. So really now I just need to look at what is happening with this limit term. So this gets a little bit tricky to consider the limit. I'm going to look at just this piece over here. So we've got the limit as b goes to infinity of e over 2 to the natural log of b. So in order to evaluate this limit, I'm going to kind of think about this differently. I'm going to use some algebra. The limit as b goes to infinity of e to the natural log of b over 2 to the natural log of b. And so what we can see here is in the numerator, e to the natural log of b is just going to turn into b. So this is the limit as b goes to infinity. I have b over 2 to the natural log of b. So from here, we're going to run through those steps because, let me think about this. We use a kind of a tricky algebra step here that you might not be familiar with for evaluating this limit. Let me rewrite this. We've got the limit as b goes to infinity. So b over 2 to the natural log of b. This 2 to the natural log of b could be written as b to the natural log of 2. That would be equivalent. So that's kind of a little trick that we're employing. So this is b to the natural log of 2. That is the limit as b goes to infinity. Now that they're the same base, that's b to the 1 minus the natural log of 2. 1 minus the natural log of 2 is a constant. And b to a constant, in this case that would be infinity to some constant number, is infinity. Therefore, the related improper integral, this guy, diverges. And if the related improper integral diverges, then the series also diverges. And that's what we need to know how to do. So the main things I want to emphasize about the integral test is when something looks easy to integrate, and this one wasn't super easy to integrate, but it wasn't terribly difficult from an integral perspective. So when something is easy-ish to integrate, we're going to then check that it is continuous. All of the terms will always be positive, and we are going to prove mathematically that it is decreasing by showing the derivative is less than 0, or by showing the nth plus 1 term is less than the nth term. And once we have proved these 3 pieces up here in the corner, then we can convert it to an improper integral. We can run through this integration process, which was kind of long. Because the improper integral diverges, the series diverges via the integral test. I hope that helps you understand that example a little better. Please let me know if you have any questions.